Okay, thank you. Thanks everyone for coming, even though it's getting late. So I'm going to talk about these combinatorial proofs of concentration bands. This is based on joint work with Jan Hasler, my student at ETH, but a lot of it is actually going to be based on a paper by Impagliazzo and Combinatorics, and I'll explain you what I mean by that. So, what's the goal of this talk? So, to explain you why I decided to talk about this, I have to tell you a little story. Okay. So in 2010, Impagliazzo and Combinatorics gave kind of, not as a main result of a paper, but kind of on the side, or also kind of it was an important part of the paper, but it was not kind of the only thing. They gave a combinatorial proof of the Chernoff band. Okay. And okay, that was nice. And then in 2011, I was working with Mark Ranzinha, who was at ETH then, and for a paper which we were working on, we needed a version of the Chernoff band. Okay, and we tried to apply this usual Chernoff band proof. Okay, so this where you bound the expectation of e to the tx, and that somehow didn't work out. Okay, and then we saw this paper by Impagliazzo and Combinatorics, and we tried to apply their proof, and it was fairly easy. Okay. And so, what I want to do today is I want to give examples of this proof, because I think it happens fairly often that we all have to prove Chernoff bounds. Okay, it happens fairly often that we have to prove concentration, and I think this proof is just not known enough, so that maybe when it's useful, that then people don't know it, and it would be easier to prove bounds using this technique. So what this means is I'm going to give you, in some sense, new proofs of old theorems. So what's the plan overall of the talk? So first I'm going to prove the basic Chernoff bound using this technique. You will see this is fairly simple. Then I'm going to prove a Chernoff bound for walks on expander graphs using this technique. I'm going to show how the techniques connects to other methods. So there is kind of a different moment-based method which is extremely similar, and you will see the connection. And finally, I'm going to say something about polynomial concentration. So let's start with the basic Chernoff bound. Okay, so here is a basic Chernoff bound. Let's say we have n random variables x1 to xn, and they're independent and uniform from 0, 1, and then the probability that you have more than n over 2 times 1 plus epsilon 1 is at most e to the minus epsilon square n over 10. So everybody has seen this. Everybody has seen a proof of this, I guess, but even if you haven't, you're going to see one now. Okay? So what's the proof idea? The proof idea is extremely simple. It can be summarized in this one sentence. Okay, so it says, oh, if the Chernoff bound would be wrong, and in fact, the probability that the random subset of size epsilon n, that the probability that it only contains ones would be too big. That's the whole idea. And if you're like me, that doesn't help you much. So let's look at it in detail. And let's give the full proof. So what we're going to do is we're going to pick these random variables, x1 to xn, and at the same time, we're going to pick a set M, which has size exactly M. So the capital M has size lowercase m. And lowercase m is going to be chosen roughly epsilon n over 4. You will see later why. And then we consider two events. So we consider the event which I call many ones. So that's the event that the number of xi is at least n times 1 plus epsilon over 2. So that's the event whose probability we want to show is small. Okay? Many ones. Then we consider a different event. I call it all in M. So that's the event that every xi, for which I is in M, is 1. Okay? All the xi in M are 1. That's why the event is called all in M. Because nobody can remember anything during a talk, or at least I cannot never remember these things. Let me put these events up here so you can always look them up. Okay, so far so good. Now, what we note is that the probability that everything in M is 1, so the probability of all in M, is at least the probability that we have many ones times the probability that everything in N is in M if we have many ones. right? So the probability that all elements in M are 1 is at least the probability that, well, first we get many 1s, and then the probability that everything in M is 1, given that we have many 1s. Okay, so what can we say about these terms in this equation? Well, the first thing here is obviously 2 to the minus m. Right? No matter how we pick m, the probability that all xi in m, which is of size exactly lowercase m, is 1 is 2 to the minus m. The second thing is, as we'll show in detail on the next slide, but maybe you can even tell now, is that the probability that everything in M is 1, given that we have many 1s, is at least 2 to the minus m times 1 plus epsilon over 2 to the m. Okay, I will show this in detail on the next slide. But once we have this, well, then we're done. Right? We cancel out the 2 to the minus m here, and we get that 1 is at least the probability of getting many 1s times 1 plus epsilon over 2 to the epsilon n over 4. Remember that m is epsilon to the n over 4. M is epsilon times n over 4. Okay, and this is exactly the Chernoff band for small epsilon. So I just want to make sure that kind of everybody sees this, because kind of it's very simple, but if you don't see this, then the rest of the talk makes very little sense, and it's late on Friday, so I don't know if I would see it. I mean, in total, it's very simple, right? We say, okay, the probability that everything in M is 1 is at least the probability that we have many 1s times the probability that everything in M is 1, given that we have many 1s, and then we know this, and we only need to bound this. So let's do this, okay? Let's go to this last term. We need to show that if m is roughly of this size, epsilon times n over 4, then the probability that we have everything in m is 1, given that we have many 1s, is 2 to the minus m times 1 plus epsilon over 2 to the m at least. Okay. So how do we do this? Well, what we do is we pick we start with an arbitrary string which has many 1s. Okay. Pick any string which has many 1s. What I claim is when you condition here on having many 1s, in fact, you can also condition on any fixed string which has many 1s, okay, and it will still be true. Okay, for this thing here, we only need the probability over the choice of m. Okay, so you pick a string with many 1s, and as a second step, you cover it up. Okay, so you forget what the string was. The only thing you remember is that it had many 1s, so that the number of 1s was at least n times 1 plus epsilon over 2. And if you're like me, then you forgot what it is. Okay? Because I didn't tell you I was going to cover it up, so now, and I was talking a lot, so now you know nothing about the string, except that previously you probably counted and saw that it had more 1s than 0s. Okay? And now we're going to randomly pick m, one by one, and uncover these. Okay, so let's pick one random, this one. So what's the probability that under this one there's a 1? Well, we know that there are more 1s than 0s, right? We know that there are many 1s. There are at least n half plus epsilon n over 2 1s. Okay, so there are epsilon n more 1s than 0. So the probability of getting a 1 is at least is 1 plus epsilon over 2 at least. Okay, and indeed, when I uncover it, I'm getting a 1. Okay, so let's look at the next one. What's the probability this one is a 1? Well, it's a bit smaller than before, right? Because we already uncovered one of the 1s, but it's still pretty big. Right? So, okay, we go on, uncovering each time being lucky. And as long as we uncover only that many 1s, right, n times epsilon over 4, then the probability of getting a 1 in the next one is always going to be somewhat big. Okay, and I picked the parameters so that in the beginning the probability of uncovering a 1 is 1 plus epsilon, but we only uncover as many so that it goes down to 1 plus epsilon over 2. Okay, so it starts at 1 plus epsilon, but then it goes down slowly, and we stop once it's at 1 plus epsilon over 2. So what this means is that each time we uncover a new element, the probability that the uncovered element is 1, given that we uncovered only one so far and that we have many ones, I should have added that we have many ones, is at least 1 plus epsilon over 2. Over 2. Okay, 1 plus epsilon half over 2. And so because we uncover m elements, the probability that all in m are 1s, given that we have many 1s, is at least 2 to the minus m times 1 plus epsilon half to the m. And that's the whole proof. So questions to this? Yes?
Not a question, but maybe a comment. So there's another proof of Schmidt, Siegel, and Srinivasan.
Mm-hmm.
Have you seen that?
Yeah.
Oh, okay.
So I will say something about this later. Actually, I forgot to mention this paper. This is from 1995. And kind of the calculations look very similar, and we will come to this in part 3, where I connect this to moments bounds. And we'll see how come it looks so different. So. Okay, so again, the proof idea in some sense is very simple, right? The probability of this Chernoff bound must be very small, as otherwise the probability that the subset of size epsilon n contains only ones would be too big. And if you are careful, then in Pagliozzo and Carbonets, they show that you can also recover, for example, this optimal Chernoff bound with relative entropy here. That's very nice, I think. Remarks, questions? Okay, let's go to random walks. So what we're talking about here is the following setting. We have given a deregular expander graph, okay? Vertices V, edges A, and second eigenvalue lambda, and I normalize things so that lambda is smaller than 1. Okay, the first eigenvalue is 1, and the second eigenvalue is smaller than 1. And we have a subset W of the vertices of density mu. Okay. And what we're going to do is we're going to pick a random walk, W1 to Wn, so like this. Okay, we're going to walk through the graphs at random, and we're going to set variables xi to be indicators whether the ith one is in the set W. And what we're going to show is the probability that the sum over the xi of the walk is at least mu n times 1 plus epsilon, that this probability is much smaller than 1. Right? So what we want to show is the probability that the number of times you are in W, that this is bigger than mu times n, okay, which is the number which you would expect on average, plus epsilon, that this probability is much smaller than W, much smaller than 1. And let me set the parameters here. So we have the set size, okay, which we want to hit sometimes. It's mu, the relative set size. N is the length of the walk, and lambda is the expansion constant, okay, which is normalized so that it must be bounded away from 1. Okay, so and then what one can show is that in this above setting, we have that the probability that we deviate by more than epsilon, in this sense, is at most e to the minus 1 minus lambda over 1 plus lambda mu over 1 minus mu epsilon square over n over 2 times 1 plus lower order terms where they are lower order in epsilon. Okay. So this theorem, again, this is not new. This was previously shown by Kahale in 1997, even though in this paper it was not stated like this. It was more stated you need to minimize some expression, but if you minimize the expression, you get this. Okay? And this is tight. Okay, so if mu and lambda, in the following sense, okay, if I say it's tight, I need to explain in what sense it is tight. So it's tight in the following sense. So first of all, kind of the best you can hope, obviously, is that the probability that this is smaller than such a thing is like e to the minus some function of lambda mu epsilon times the number of steps in the random walk times n. Okay, so it's e to the minus something times n, because it cannot go faster down than n. Okay, and now this function, what we claim here, this function in front of the n, what we say here and what you can show is that this function, if you make epsilon smaller and smaller, the dominating term in epsilon is 1 minus lambda 1 plus lambda mu 1 minus mu epsilon square half. Okay? So there are other terms which are not important if epsilon goes to 0 faster kind of than lambda and mu. Okay, if you think of lambda and mu as a constant and you make epsilon very small and then n very big, then this is tight. Okay, and what we do here is we use this Impariazzo-Cabanets technique and show that indeed you can prove this using this technique. So even tight expander walks can be proven like this. So here's the theorem, okay, which I kind of want to sketch the proof of in the talk. So we kind of imagine that we set mu and lambda to be constants, and then what we want to show is that the probability that the sum of times you hit the set, the probability that this is more than mu n times 1 plus epsilon is exponentially small in n. And what we're going to do is we're going to use the same technique as before. So again, we have these two events. Okay, the probability that you have many ones, which is again this thing. The probability that for a random set M of some size that everything in M is 1, okay, which is this event here. And we're going to write down the same equation as before. Very simple. So we say, okay, again, the probability that you hit everything in M is at least the probability that you get many ones times the probability that you hit everything in M if you have many ones. Okay, now let's analyze these terms. So it turns out that this one, right, with this covering proof which I gave before, it's exactly the same. The probability that everything in M is hit, given that you have many ones, is still going to be at least mu to the m times 1 plus epsilon over 2 to the m, as long as m is smaller than kind of epsilon m n over 4 or something, and this certainly makes m small enough, so this is simply true. Okay? So the only thing we have to worry about now is the probability that everything in m is 1. Okay, so now the setting here is we make a walk on an expander, and we pick some of the steps. Okay, we uncover some of the steps, and we look, okay, are we in the set in these steps? And what we want to show is that the probability that all of these are in the steps is not too big. Okay? And so for this we have this lemma. So suppose that you pick a subset M of 1 to the n at random, then, and of this exact size, then the probability that everything is in M is roughly mu to the m. I'm ignoring some terms depending on epsilon, which I will fill in later. Okay, so if m is not too big, then in these you have this. I'd like to quickly sketch how to prove this lemma. It's not too difficult, but I will still not do the whole proof. So this is the lemma again. Suppose we pick this set at random and make that many steps, then the probability that all of the steps land in the set M over the choice of the set M and the walk is at most something like mu to the n. So how do we do this? Well, let's first understand this probability in case the set which we pick, right, the position in the walk which we uncover is fixed. Okay, so let's suppose that the set is fixed M, and let's write it in this way. So the first element in the set is D1, okay, a positive number. The second element is D1 plus D2. Third element is D1 plus D2 plus D3. The last element is D1 plus and so on plus Dm. Okay, I can always write the set in this way. So what I claim is, if you now fix this, okay, and you take the probability over the walk only that everything is in M is at most this product over mu plus lambda to the di. Okay. And how do you prove this? Well, you go and you look what other people prove, and they prove this. Okay. So this is something which is kind of a hitting property of random walks. Okay, so it's well known that this is this bound. I forgot to write down the reference. So does someone know who proved this? Yeah. But it's an old result. It's very well known. It's kind of you do a spectral technique, so you just look this up and you know this. Okay? And this Komloschen Semeredi. I see. Sound, yeah. Okay. So this is well known. You kind of just you just write the kind of the probability distribution in the ith step as a vector, and you apply kind of you do eigenvalue decomposition, and then you don't have to do so much work. So what does this mean? So what this means is that what we need to show is that if we pick the set M at random, right, that basically the expectation of this expression over the choice of the set D is small. And that's all we need to do to get Chernoff bounds for random walks on expander. Okay, all we need to do is to show now that the expectation of this expression when we pick a set M is small. And so, okay, this is all we need to do. And this would be very simple if the DI were independent, because then what you could do is you could just exchange the sum and the product sign, okay, and you could kind of understand each individual term, and the individual terms are kind of so that it's kind of obvious that they are small because they are way bigger than, kind of they are in expectation way bigger than 1 over 1 minus lambda. And so kind of if they were independent, then it would be obvious. However, they're not independent, right? They are kind of picked by this process. And in particular, if DI1 is huge, then the next one are going to be small. So they're not independent. But don't despair, okay? So we can always replace the DI with something smaller, and that doesn't break the bound. Okay? Kind of if we make fewer steps on the random walk between two uncovered things, then this only makes the probability worse for us. Okay? If we kind of reduce the steps. And what you can show is that there is a joint distribution of D1 to Dm and C1 to Cm, some random variable C1 to Cm, so that the Ci are indeed smaller and they are independent and they have a good property. And that's a fairly simple thing. I mean, it's kind of very clear how you do it. You need to couple these two things and you get this bound. So you need to think about it. And I thought, okay, should I show this? And I decided it's more technical than insightful. So I omit the proof of this. But it's kind of an exercise. Okay?
Can we use negative association?
I didn't check that. I mean, it was not hard enough for me to check that. It's fairly easy to prove, so you just prove it without even looking at tools. I'm sorry, I don't know. Good, so now once you have this, what you can say is, okay, the expectation over these M of these mu plus lambda to the Di is at most the expectation over M of the Ci, where you kind of pick the Ci together. Then you exchange the product over the sum, and then you get this. Okay, so let's look at it again. So the overview really follows for expander walks this simple recipe. So you do this main step, okay, you say, the probability that all in M is at least the probability I get many ones times the probability that all in M given any ones. Then this left-hand side is just the hitting property for expander walks, which is well understood and very easy to bound. And the right-hand side, they just use the randomness over M. Okay, now let's go to part 3. So this is connection to moments, and where I hope to answer Anoop's question. Let's see. So what did we do? We started with this basic inequality. Okay? The probability that all in M is at least the probability that many ones times the probability that all in M given many ones. And of course what we really did is we kind of just bounded the probability that you have many ones by this quotient. Okay? And what we said, especially in the second part, is okay, this lower part here you can basically always bound by mu to the M 1 plus epsilon to the M, or epsilon half to the M. And here I write epsilon half to the M. So basically this was the basic inequality which we used. Okay. And the statement was just kind of, okay, if you can bound this, then you get the good bound. In many cases, an optimal bound. And now another technique, and here I reference this paper by Jansson, Olieszkiewicz, and Ruczynski, but I think this SSS paper from 95, as Anu points out, they do the same thing. So kind of what they do is, okay, let's look at this probability which we want to bound. And let's just say that we take everything on both sides to the power of m, for some m which we can choose later. Okay? So you can do that. It's going to be the same probability. And now let's do Markov. Okay? So using Markov's inequality, you get this. Okay? So this means that the probability you get many ones is this expectation of 1 over n to the m times the sum of xi to the m. So that this is a typo, it should be sum xi to the m. Okay, the sum is taken to the mth power, like here. So let's compare the two expressions. Okay. You see they look fairly similar. And why do they look fairly similar? Well, what's this sum here? What's this expectation over sum over xi to the m over m to the m? Well, we expand this sum in here, and we get that it's 1 over n to the m times the sum over all indices e to the xi to e to the xim. Okay? So now this, okay, you can imagine that's like picking a set of size m at random. Okay?
With repetition.
But with repetition. Okay? Here now you pick with repetition. And then this expression, if we have 0, 1 random variables, it's just exactly 1 in case all of the xij are 1. Okay? It's exactly the same except with repetition. Okay, so this kind of shows that there is this connection. And I think the SSS paper, maybe you know better, but I mean they just adopt this view. Okay. Of course, this is kind of, it leads to very similar things. And so what this means is that two techniques are almost the same, but this Impaliazzo-Cobonetz's trick, okay, that's kind of one advantage in my opinion. It's very simple to understand, right? I mean, this very basic thing is simple to understand, and I find it very intuitive. The other thing is also simple to understand, but I just find the mth moment a bit less intuitive. And one more advantage which we exploit in the expander random walk proof, for example, is that you have choice how to pick m. So you can either choose it with repetition or without repetition. And it's not the same, okay, because if you look at the lower side thing, if you pick m without repetition, then it's always going to be 1 plus epsilon to the m here. And it's not going to go down. If you pick it with repetition, it's going to go down. Okay, so it's not exactly the same. And for example, in the expander walk technique, it seems easier to work without repetition, and then it seems easier to work with kind of this view. Okay. However, at the moment, it's easier to generalize if the xi are not over 0, 1, right? I mean, kind of this all in m thing, this only makes sense if the random variables are 0, 1 random variables, and otherwise you have to work something. So at the moment, it's easily generalized. Okay, so I have some time left, I think, but not really. So I will skip the polynomial thing and come to the conclusions. So what I just wanted to show you is this Impaliazzo-Cobonetz's technique, which is kind of a very, very simple thing, which in my opinion gives a nice way of proving concentration bounds, which I find very intuitive, and at least kind of for me it's the way to teach them in class. And the technique is still powerful, right? It can be used to give tight bounds for random walks on expanders. And in some cases, that's the one I told you about in the beginning, it at least to me seems easier than bounding this expectation. And however, there is a very close connection of the technique to bounding the mth moment. And just as a side remark, we have some reproving of other bounds using this technique. Thank you.
Just a small comment. Somewhere I have a one-page note where we show that you can eliminate the assumption of independence in the Impaliazzo-Cobonetz's.
Yeah, I mean, this is... so what do you do instead of independence?
No assumptions.
Well, you need some assumption to... I mean, so we kind of the reason why we needed this other proof, this proof in the paper with Macron is also because we did not really have independence. And so we needed to eliminate this kind of.
It's an even shorter way.
But yeah,
This is also the point of the SSS paper. So the only assumption I need then is that every set of size m, the probability of getting all ones is small. That's the assumption I use instead of independence.
I could not find this like this in the paper, but maybe I did not look at it exactly enough. Okay, but.
What was the statement of the polynomials that you were going to tell us about?
Oh, yes, okay. So that's from the abstract, or what? I mean, just, no, this is, okay, so, yeah, I don't even want to show it so exactly. I mean, there is this paper by Kim and Wu in 2000, where they say, okay, if you have a polynomial, then under certain conditions, which I don't want to go into now, the value of the polynomial is concentrated. Okay? And using this technique, you can relatively easily reprove this with kind of somewhat different bounds, at least. However, kind of there is papers from 2012, for example, where they prove it using the old technique with optimal bounds. So it's kind of, I don't want to go into it without more time.